Hello everyone. In the last couple of videos, we have been discussing the Black-Litterman model. In this video, we are going to use some data and implement this model. Let us first of all have a quick look at the formula that we have been discussing in the last videos. Well, this is the formula here, and we are going to talk about the second term briefly, which is nothing but a weighted average of pi, which is our implied equilibrium excess returns, and Q, which are our views. Both the pi and the Q have been multiplied by their respective weights. The weight on pi is this item here, tau times S inverse, where tau is a scalar and we have agreed to use a value of 1 for it, and S is the variance covariance matrix. The weight on Q is this item here, P transpose times omega inverse, where P is the link matrix and omega represents the uncertainty of our views. The first term, this one here, is simply used to force the weights to sum up to 1. In class, we have already implemented the Capm model for 6 companies. Let me go to that worksheet to refresh your memory. Well, this is that worksheet here. We have taken 6 companies: Bank of America, Ford Motor Company, Netflix, Illumina Incorporation, GTX, and well, this fold is a ticker symbol for Amicus Pharmaceuticals Limited. We also had the data for S&P 500 and the T-bill rate. And in this section of the worksheet, we had calculated the log returns by using the monthly prices for a period between February 2008 and it ran up to December 2011. We had then gone on to compute the excess returns in this section of the worksheet, where we had subtracted from the log return our risk-free rate or the T-bill rate. And after that, we had computed the historical average returns on all the stocks and the market. We had computed the alpha value and the significance. We had also computed the beta value and the significance, and then we had gone on to the predicted returns as per the Capm model here in this row. We are going to use the same data in this demonstration for implementing the Black-Litterman model. So let us first of all look at the list of inputs that we need to implement the Black-Litterman model. What we need first of all is this item here, price of risk, which we can also call the investor's risk aversion, and we have given it a name A. We need the variance covariance matrix S. We need market weights W, which we are going to establish by using market capitalization of the 6 companies that we are using. We will also then arrive at the vector for implied equilibrium excess returns, which we have decided to call pi. We are going to have to incorporate some views, which are going to be in a vector Q. Then vector Q has to be connected to what the views are about through a link matrix, which we call P, and then we are also going to have a matrix that represents the uncertainty about our views, and that would be called omega. So let us quickly get going by first of all calculating the parameter for risk aversion A. To calculate A, we can use this formula, where on the numerator we have the excess market returns and on the denominator we have the variance of market returns. So we have these 2 time series already here, which I copied and pasted earlier from the master worksheet. In this time series we have the excess returns of the market, and in this time series we have the raw log returns of the market. So let us first of all calculate the excess average market returns over the time period that we are using from February 2008 to December 2011. So let's calculate the average excess returns by selecting this range of data. Well, this is a negative number and it's going to give us a negative value for A, which is not going to be too intuitive. Alright, we'll talk about it when we get there. Variance of market returns, so we can calculate VAR, and then we are going to select this series for the raw log returns of the market. Well, this is the variance of market returns, and now we can calculate A, which is excess average market returns divided by the variance of market returns. and what we see is a negative value for A. Well, this is not so intuitive then. If investors are risk averse, they would be seeking a positive excess return per unit of risk. Rather, we are seeing a negative number here. Well, one way to look at our negative value is to believe that investors have been probably seeking risk during this time period. But I personally feel that this would not be a reasonable belief, given the market conditions in the recent past. We could also say that since market returns have a variance, the returns are likely to move into a positive zone anytime, and perhaps the investors have been willing to tolerate negative returns in the hope of future positive returns. Well, this may be so, but I certainly am not one of those investors. What I believe, the most likely reason to me seems to be the fact that our data set is limited to a time period where the markets have been in the red more often. The theory predicts a long-term average value of somewhere between 1 and 10 as the risk aversion parameter. And if we include enough data that smooths out market cycles, maybe we would be able to confirm that. For this reason, we are not going to read too much into the significance of this A in our demonstration. We are going to just use it for a computational purpose. Well, if this does not feel right to you, you can use a positive value for A in your own analysis and see what difference that makes to your results. Well, you are going to find that your implied equilibrium excess returns will then be positive, and then that may again be questionable for the time period that we are using. What I'm going to do is to stick with the result that this data set gives me, because even if it is counterintuitive, it's the only truth there is at the moment. So let me now go over to the next step where we need to compute the variance covariance matrix. So I'm going to change the worksheet. Well, in this worksheet, I have reproduced our log returns for the 6 companies that we had calculated before. All these 6 companies and their log returns going down till December 2011 and starting from February 2008. And here, let us compute the variance covariance matrix. How we do that is by going to this tab, data, and then clicking data analysis, and we are going to now select covariance, say OK. We are going to provide the input range, which starts from here. So let me select my data range. Alright, I'm going to say give me the labels in the first row, and then I'm going to say give me the output within this worksheet, well, in cell H1 here. So, well, that's okay. Let me click OK and see what we get. Well, we have the variance covariance matrix here, but Excel has omitted this region here, so we are going to have to manually fill in the values. So let's complete this row by selecting these values, and I'm going to paste them here. Paste special transpose. Then I'm going to select this region here and paste special transpose. Then I'm going to select this region and here paste special transpose. Then these 2 values copied, and we have to paste them here, and then this value copied and pasted here. So this will complete our variance covariance matrix. Before we forget, let us give this a name, because we are going to use this matrix later. Let's call it in the name box VAR underscore COVAR underscore matrix. Okay, so this is done. Let us now move over to the next worksheet. Where we are going to begin with the Black-Litterman workings. Well, here in this cell, I'm going to just copy the value of our risk aversion parameter. Where is that? Risk aversion parameter is here. So I'm going to copy this and paste it here. I'm going to say paste just the value. Alright, earlier I had gone to Yahoo Finance and noted down the market capitalizations of my 6 companies here. These are the market capitalizations in $1 billion. So what I'm going to do here now is to total up all the market capitalizations. Sum. What we are doing is basically we are trying to calculate the market weights. We are assuming that the market consists of only these 6 stocks at the moment, to keep it simple. So, well, we are taking the sum. So this is the total of all the market weights here for all these 6 companies. Now we can calculate the market weights by simply dividing this market capitalization by the sum of all market capitalizations. Because the denominator is going to remain the same, I'm just inserting a dollar sign so that I can then drag and drop the formula. Well, these are our market weights and they add up to 1 here. So this is done. What next we want to do? We want to, before we forget, let us give this a name as well. This region is our market weights, so let's call it MKT underscore WT, market weights. Alright, now we are ready to calculate the implied equilibrium excess returns. You will remember from previous videos that implied equilibrium excess returns are equal to the risk aversion parameter times the variance covariance matrix times the market weights. Well, this R is the same thing as the pi. So I'm going to have my implied equilibrium excess returns into this column here, this vector, by entering this formula. What I need to do is that I need to multiply A, which is here, with the product of 2 matrices. The first matrix is my variance covariance matrix, so I'm going to say M mult variance covariance matrix, and my second matrix or the vector is going to be the market weights, so I'm going to say market underscore weight close brackets and hit Control Shift and enter. So these are the implied equilibrium excess returns. Black and Litterman said that we don't need to maximize the investor's utility function. If you will recall, we discussed that in a previous video. We don't need to really maximize the investor's utility function for optimum weights because weights are observed in the market. So that's why we have used market capitalizations, computed the market weights, and then we have gone a step back. We have reversed the problem basically. So by using the market weights, we have computed now the implied equilibrium excess returns. And now let us see how to implement the Black-Litterman model. Well, this is the formula again, but to implement it we need a few more inputs. First of all, we need to have some views. Well, if we don't have any views, we can just use these returns, and by using these returns we can use our standard optimization techniques to construct an optimum portfolio. Basically it would be just the market portfolio because it's going to track back into market weights one more time, because it is on the basis of the market weights that we have gotten to these implied equilibrium excess returns. So if we believe in the market, we are just going to hold the market portfolio, and that would be it. But then if we have some views, let us make up some views. Well, this is not an investment advice. I'm just randomly making up some views. Well, let's say that Amicus Pharmaceuticals is going to outperform GTX by 0.5%. So that's our first view. So let's write here 0.5%. So 0.005. Let us also fill in the values into the link matrix side by side. We say that all positive views in the link matrix have to be entered as a +1 and all negative views have to be entered as a -1, so that the sum of all relative views is equal to 0. So our first view that we are using is that Amicus Pharmaceuticals, where is that? Here is Amicus Pharmaceuticals. We have a positive view about it, so we write a 1. We said that Amicus Pharmaceuticals is going to outperform GTX, so we are negative about GTX, so we enter a -1. and the first view says nothing about the other stocks, so we enter zeros for them. Let's make up another view. Let's say Illumina Incorporation is going to outperform Netflix by 1%. Well, these are just random views from the top of my head. Illumina Incorporation is going to outperform Netflix. So let's give it a value. Let's say 1%, so 0.01. Illumina Incorporation, we are positive about that, so 1. And Netflix, we are negative about that, so -1 in the link matrix. All other cells would be 0. So let's quickly fill them up. Let's also take a third view. Let's say that the Ford Motor Company is going to outperform Bank of America by half a percentage point. So let's say 0.005. And what are we positive about? We are positive about Ford Motor Company, so we enter a 1. Negative about Bank of America, -1. And the view doesn't talk about any other stock, so all other items are 0. So we have this is our Q vector, views vector. Let's give it a name, Q. This is our link matrix. Let's give this a name, link matrix, P. And we also had figured out the implied equilibrium excess returns before. This was that region, so let's name this one as well. This is our pi. Okay. Now let us see what else we need. We need to figure out what is omega. Omega, if you will remember, is the uncertainty about our views. And Black and Litterman suggests that we can compute omega by using this little formula here, tau times p times s times p transpose, and tau we have assumed it to be equal to 1. So omega now in our case is going to be a matrix of what order? We have 3 views, so it's going to be a matrix of the order of 3 by 3. So let me select that region, 3 by 3, and we are going to have to do some matrix multiplication. Well, tau is 1, so we ignore that. What we need to do now is to invoke the mmult function. What are going to be our 2 arrays? The first array is going to be a product of 2 matrices, P and the variance covariance matrix. So I'm going to write here P. Inside we are going to have another multiplication, so multiplication between P and variance underscore covariance underscore matrix. This is it. And the second array is going to be the transpose of P. So let me write here transpose transpose of P. So this is done. Let's see if we have closed all the brackets. Well, we have closed the bracket for transpose, but we have to close the bracket for the mmult function still. We do that and then hit Control Shift and enter. So well, this is our omega, which is giving us the uncertainty about our views. Now this Black and Litterman formula is a long formula, so it would be convenient if we break it down into 2 parts. It's a product of 2 terms. We can solve the first term first, and then we can solve the second term, and later we can multiply out those 2 results. So let us solve the first term first. Okay, so here we have the first term. It's going to be, there are 6 companies, 6 stocks, so it's going to be a 6 by 6 matrix. So let me select this region, and what do we need to do? We have to take the inverse. So I'm going to write M inverse, and now we have to provide the array. Inside the array, what do we have? We have the inverse of S first. So I'm going to write here again M inverse of our variance covariance matrix, VAR underscore COVAR underscore matrix. What else we need to do? We need to add the product of these three matrices here. So I'm going to have to invoke the mmult function again, mmult, where my first array is going to be the product between P transpose and omega inverse. So let us see, mmult again, and what we have, transpose of P, TRANSPOSE, transpose of P. That is done. What's the next? We have to take the inverse of omega. So M inverse of omega. We didn't name omega, did we? Alright, so we can select this region. So this is our omega. Let's see if we have closed the brackets. M inverse of omega, close the bracket for this mmult, and then we have to provide the second array to our original mmult function, which is P. The second array is P here. If you can see here, this is P, and so we write a P here, and we close the bracket for this mmult function, and now we have to close the bracket for the outer M inverse function. So we have closed that, and let us hit Control Shift and enter. Alright, so this is our 6 by 6 array for the first term. Now let us figure out the second term. Well, this is the second term. It's going to give us a 6 by 1 vector. So let me select this 6 by 1 region here, into which we are going to see what we need to do. First of all, we need to have a multiplication between S inverse and our implied equilibrium excess returns. So I'm going to write here mmult, and then what are my arrays? My first array is the inverse of the variance covariance matrix, so I'm going to have to write M inverse of variance covariance matrix. Okay, and what is the second array? The second array is pi. So we can close this bracket now for the mmult. What after that? We have to add now, so I put a plus sign, and then we have another matrix multiplication of three matrices. So we are going to have to use mmult function twice. So let me say here the outer mmult function first, and then inside I have to provide my arrays. My first array is the matrix product of P transpose and omega inverse. So I'm going to write mmult transpose of P and multiplied by omega inverse. So I'm going to write M inverse. We didn't name omega before, so we are just going to select the range. This is our omega matrix. Let's see if we have closed the brackets. Well, for the inner matrix multiplication, we now close the bracket, and then for the outer mmult function we have to provide the second array, which is going to be our views vector Q. We didn't name Q either. Okay, so where are our views? Well, this is Q. That's it. And now we are going to close the brackets and hit Control Shift and enter. So here we have the second part of our Black-Litterman formula, a 6 by 1 vector. All that we need to do now to calculate the Black-Litterman expected excess returns is to multiply out, well, this matrix here with this vector here. So let's do that here in this region, this 6 by 1 region. So we are going to select our first matrix, this one. I didn't put in the mmult function, so let's do that. mmult, and this is our first array, comma, and the second array is this one here. Control Shift and enter, and here we have the excess returns as predicted by the Black-Litterman model. Well, how do they compare with the historical average returns and Capm returns? Well, Capm returns are pretty far off. If you see, 1% for Bank of America, negative 1%, but negative 5% as predicted by the Black-Litterman model. This is pretty much close to our historical average. If we look at Ford Motor Company, Capm predicts minus 1%, but Black-Litterman says 4%, and the historical average is about 0. So there are some differences in each of these returns, and that is the problem with the portfolio manager. Which returns would be good for optimizing a portfolio? Which returns to use as an input into the portfolio optimization process? Well, we have seen historical returns are pretty close to the Black-Litterman returns in this case, but Black-Litterman returns are sensitive to our views. If we changed our views, we would have different values here. Let's see if they are making sense according to our views. What views did we have? Well, our first view was that Amicus Pharmaceuticals is going to outperform GTX. Let's see if we see that. Amicus Pharmaceuticals is here, negative 1.5%, and GTX is negative 1.8%. So, well, all are negative, but Amicus Pharmaceuticals is slightly closer to 0 as compared to GTX, so it is slightly better. So that is reflecting our view. What other view we had? We had this view, second view, that Illumina Incorporation is going to outperform Netflix. So let's see. Illumina's returns almost 0, minus 0.0056. And what was the view about? Illumina and Netflix. So Netflix is here. Well, it is more negative, negative 1.3%. So our view is reflected. We had this one, third view, where we said that Ford Motor Company is going to outperform Bank of America. So let's see the returns for Ford Motor Company, minus 4.63%, and Bank of America minus 5.37%. So Ford is a little less negative than Bank of America. So this is how we can compute the Black-Litterman returns, and then use our standard techniques for optimizing the portfolio based on these returns. This is all I wanted to cover in this video. I'm already running close to half an hour, so I guess I'm going to close this session here. Thank you so much for watching. See you later.